What if the next data center isn't built in Silicon Valley, but 500 miles above Earth? Every day, satellites capture massive amounts of data, from climate patterns and disaster zones to military intelligence and global communications. But there's one huge problem. Getting all of that data back to Earth is slow, expensive, and limited by bandwidth. That's where space data centers come in. In this video, we'll explore how orbital computing could let satellites process data directly in space, how laser links and satellite networks could form a space cloud, and what challenges still stand in the way, from routing around the sun to keeping these systems reliable in orbit. By the end, you'll understand why cloud computing may not stay on Earth forever, and why the future of AI infrastructure might be floating above us.
Welcome to today's Explainer. We're jumping right into something that honestly sounds like it's straight out of a sci-fi novel, but it's literally being engineered as we speak. Today, we're unpacking the incredibly complex network architecture and routing strategies behind space data centers. If you've ever wondered how the massive, invisible infrastructure floating right above our heads is going to evolve to handle the next generation of space tech, well, you're in the right place. Okay, let's dive into this. Picture the sky above us by the time we hit the 2040s or 2050s. We're anticipating tens of thousands of satellites in orbit. Tens of thousands. It's kind of hard to wrap your head around that sheer scale, right? Because private sector innovations have completely slashed the costs of building and launching satellites, we're facing an unprecedented surge. But here's the catch. All those new satellites doing high-resolution Earth observation and environmental monitoring, they're creating an absolute mountain of space-generated data. And that brings us to a massive billion-dollar logistical hurdle. How do we actually get all that data back to Earth? It sounds like a simple A to B logistics problem, sure. But the reality, the immense volume of data we're talking about makes it increasingly costly and technically exhausting to beam everything down to terrestrial data centers. We are rapidly speeding toward a massive Earth-space data bottleneck. Let's break down why our current methods are totally failing us here. Satellites in low Earth orbit are moving incredibly fast. They only get these tiny, brief windows of visibility, literally just a few minutes per pass, to talk to a ground station. And building more ground networks, hugely expensive. On top of that, our traditional radio frequency spectrums are completely jammed up. Now we could use high-speed optical lasers to beam data down, but guess what? A cloudy day over the ground station completely blocks the transmission. It's kind of like trying to download a 4K movie on a spotty, overloaded 3G network. We just can't rely on beaming raw data down anymore.
So the crucial point is, we need to rethink the architecture completely. Enter the Space Data Center, or SDC. At its core, this is a software-driven, multi-tenant AI platform. The genius solution here is that instead of bringing the data to the data center, we put the data center up where the data is generated. Think of an individual SDC node out there as being just like a server pod in a normal Earth-based data center. It's got the compute, the storage, and the networking, all bundled into one highly efficient unit operating directly in orbit.
Here's how it changes the game. Instead of hundreds of individual satellites fighting for a clear window to beam down heavy raw data, they bypass the bottleneck entirely. Client satellites just zap their raw data over inter-satellite links directly to an SDC node in orbit. That node uses powerful onboard AI to crunch the numbers, say instantly identifying the exact coordinates of a wildfire from a massive image, and then it sends only the tiny, low-latency, actionable insight back to Earth. It's a beautifully elegant fix that absolutely slashes transmission overhead.
Zooming in, the constellation topology. Let's take a look at how these nodes are physically arranged out in the vacuum of space.
And this brilliantly illustrates the foundation of the whole thing. It relies on shared orbits. SDC nodes that share the exact same orbital path form what's known as a pseudo-static ring. Because they're cruising at the exact same speed on the exact same track, their relative positions basically never change. They act as this highly predictable, tightly coupled network cluster. To put a number on it, a proposed benchmark for this features 200 satellites spread across 20 distinct orbits, meaning you get 10 satellites locking in each of these stable rings.
But, a single ring doesn't give you a global network. These individual rings have to establish dynamic connections with nodes in other rings, specifically right at the points where their orbits cross. This is where the routing gets seriously sophisticated. By handing data off horizontally between different orbital rings, the system can seamlessly balance heavy computational workloads across the entire constellation. It ensures uniform global coverage without ever overwhelming just one node.
Free-Space Optical laser links. Basically, the fiber optics of space. Let's look at how the network actually talks.
To really appreciate why these free-space optical or FSO lasers are such a game changer, we have to look at the legacy tech. Radio frequency has been our reliable workhorse for decades, right? But it's got strict bandwidth limits, high signal loss, and terrible spectrum interference. FSO lasers, on the other hand, they shoot incredibly narrow beams to deliver massive data rates over huge distances. It allows these orbiting data centers to talk to each other privately and lightning fast without clogging up the already packed RF spectrum.
Zooming in even further to the actual routing hardware, the network relies on two totally different types of routers to juggle this traffic. First up, dynamic routers. These guys handle the messy, constantly changing, temporary links connecting to passing client satellites or down to ground stations. Then you have the heavy lifters, quasi-static routers. These are hyper-capable systems dedicated purely to interconnecting the SDC nodes to each other via those high-speed lasers, essentially orchestrating the massive workloads across the whole constellation.
The routing villain's solar stray light. Because, hey, space is rough, and even a perfect laser network has a nemesis.
Now, what's really interesting about this whole setup is the geometry problem. There's a 30-degree cone, a solar whiteout zone facing the sun. These FSO laser receivers are ridiculously sensitive, so if an SDC node's orbital path points its receiver within 30 degrees of the sun, it's essentially staring down a flashlight. The terminal has to completely shut down its receiver to prevent permanent optical damage. That creates a highly predictable but totally massive rolling blackout for data links across the network.
So how in the world do you route around the sun? The engineering here is actually brilliant. The network has to be incredibly smart. The second a node detects it's hitting that 30-degree solar danger zone, it kills the forward-facing terminal. The system then dynamically pivots. It can trigger a reroute, literally bouncing the data the long way around the orbital ring in the opposite direction to bypass the blind spot. Or, if the data isn't incredibly time-sensitive, the router just dumps it into deep caching memory, buffering it safely until the satellite clears the sun and the laser boots back up.
Let's move to and see how this builds out into something much bigger. Once this robust, dynamically routed architecture is humming along, it unlocks what we call the future space cloud. Just like AWS or Azure down here on Earth, we're talking about familiar cloud business models emerging directly in low Earth orbit. Infrastructure, platforms, and software, all as a service. It completely democratizes space data. Now, smaller companies can run complex AI on space data without having to launch their own multi-million-dollar satellite network.
I really want to emphasize this powerful takeaway from the source material. Look, deploying actual data centers into space requires a massive upfront investment, for sure, but the research points to one undeniable fact. Ultimately, performing most computations and AI algorithms in space will be far more cost-effective than trying to beam all that raw data to the ground. Edge processing up in orbit isn't just cool tech, it's the definitive economic solution to the bottleneck.
Which leaves us with one final, pretty profound question. Are we ready for cloud computing in the stars? Because this isn't just an idea on a whiteboard anymore. Right now, the foundations are being laid for this invisible, laser-connected web orbiting right above our heads, a network that is going to fundamentally change how we process and understand our world. I hope this explainer helped you visualize exactly how this orbital architecture comes together. Keep looking up, keep learning, and thanks so much for exploring the incredibly cool world of space data centers with me.